plus y equals y plus x. Obviously, blatantly true, right? So, that's line 1. We're going to be trusting we only need the one induction, because that's usually the case in this course. We know that there's one induction, we only need the middle quantifier. So the first quantifier we'll just get rid of in the old traditional way, so that's reasonably safe. A plus y equals y plus a. I need a handwriting in that for this proof. And this is going to be by induction. So this a plus y, we're going to change the y to an n or an s of n and try to prove that. Okay, so you're going to try to prove a plus s of n equals s of n plus a. We'll try to prove that from assuming a plus n equals n plus a. 1, 2, 3, 4, 5. Just making sure that we put all this in. 5, 5. Just up another 5. Another 5. I don't think we need all of this room, but we're going to need some of this room. So we're going to assume a plus n equals n plus a. I'm going to try to prove that. So I've got myself 20 lines there, which is probably more than I need. 4, 6, 10, 14. Yeah, I think I need only like 18 lines or something. So that looks hard. If we look at the top first, we'll get back to this. Line 3. A plus 0 equals 0 plus a. Now, I want to prove that. Any thoughts on how I'm going to prove that? That's the easy one. Any thoughts? We've done something a bit like that. So we can't break down this a in any way, so we can't do much with that. But we could say if there was a universal rule, we'd be sweet. So let's hope that we can prove that rule. This will be line 6. And then from line 6 we can get line 3, just by universal elimination. So now we get to prove that. Well, that's easy enough. That's a universal. If we just did universal elimination, we end up with that again. So we're not doing universal elimination. We're going to be doing the other universal rule, which is induction. So we're doing an induction inside the induction because that's how life works. So I guess that's going to be from 7 and from 8 to 9 and induction. Okay, so our 8 to 9, our bottom line here will be this without x being an s of, let's say m, so we don't confuse with our earlier m. S of m equals 0, it's the same as 0. So Sm plus 0 equals 0 plus Sm is what we want to try to prove. And we're going to assume, let's give ourselves, I don't know, 7 or 8 lines. 8. Good. We're going to assume m plus 0 equals 0 plus m. Also, of course, we need to prove line 7. This is the big one. So, line 7 we can prove. That something equals itself. Good. We've got the base case of this induction. Now we need to do the inductive step, the second step of the induction, which will give us this, which will give us our base case of our original induction. So we're just doing this first induction to prove our base case here. Okay, S of n plus 0 equals 0 plus S of n. Well, that's just an identity, so we'll just do a big identity block. That's, I guess, 10. F of n plus 0. Well, that's S of n by Q3, which is S of n plus 0 by Q3. Why did I do that? So I could use my n plus 0 result here. I wanted to use that already. That's S of 0 plus m by this rule here, by line 8. And now I can put my S back inside. 0 plus S of n by Q4. And that's what I wanted to prove. So now I have proved that both when I'm adding 0 and I'm adding S of n, any number plus 0 is equal to 0 plus any number. So I've used induction inside that to prove my base case. My base case is true, my case with 0 here is true. I have used induction to prove that. I've now done 3, which is the first part of my proof. A plus anything is equal to anything plus A. Sorry, A plus 0 is equal to 0 plus A. Now we're going to go back to the bit at the bottom that we skipped over. Leave that there people to copy for a moment. We're going to be assuming this and proving A plus S of n equals S of n plus A. But I'm going to leave that first bit up there. I don't think there's any tricks there, except we had to use induction. But I hope you're starting to realize that x plus y equals y plus x is not a thing you can just go around assuming. Okay. Can I scroll up? Now we need to prove this from that. Well, that's not so bad. This is just an identity. So we just need an identity block. Let's not get carried away with a nice small identity block in case we need to do some more work later. And so we want to show A plus S of n. We want to try to get down to that being S of n plus A. If we do that, then by 11 we get the block we want. Oops! Going up here, we got the line, and that is from line 10. We did a density introduction. 10. Okay. Right, so if we can fill in this, then we're done. Yay! A plus S of n will move the S out in the front. Maybe we won't need this space. By Q4. And now I can use my assumption up here. A plus n equals n plus A. S of n plus A by line 4, which is not Q4. And now I just need to move that S inside the bracket. That doesn't seem that hard. But the rule only allows us to move the S back in here. That'll be n plus S of A. Going from here to here looks like there's a problem. So what rule do we need to be able to go from here to here? Let's write that rule down. See if it's a sensible rule. For any number you have, S of, is that rule right? I'm going to say S of n plus
A
x, thank you, equals S of n plus x. If I had that, then I'd be sweet. That's true for any x. This is an arbitrary a, so we need to make one true for all of them. If we have this rule, let's call it 12, I guess, up to 12. So 12 would be sweet. So all we should do now is prove this rule. Before we try to prove it, we say, does it make sense in math, in case we're trying to prove something crappy? The successor of two numbers is equal of n plus x is equal to the successor of n plus x. Cool, doesn't matter if you add 1 to the whole thing or 1 to one of the numbers before adding them, that should still work. It should be provable. So let's just try to prove that. Well, it's a universal. We could use universal elimination, but that's going to give us what we're trying to prove. So that won't help. You have to prove what we're trying to prove. So instead, the other thing for universal introduction, it's induction time. Okay, well, I'm excited. So we're going to do another induction. This has been an exam question, this particular one in the past. This is like the harder of the exam questions. And we would have said something like, hint, you might have wanted to prove this and the other induction thing above. So saying if you can prove those, you can prove this bigger one. This might seem crazy. This will be like one of the questions for splitting out the A minuses from the A pluses, but it is a reasonable exam question that has occurred in the past. And it's just lots of little inductions. My eyes are getting worse. I'm going to try to read my handwriting. Cool, it's focused now. It's bad, but it's focused. Okay, so we're going to need to prove S. Now we're going to be doing inductions on this N. This X. So I guess we use an N and an N. I'm just going to use P for our induction one now, just so we don't get confused. S of N plus P, here's what we're induction on, is equal to S of N plus P. S of P, what are the terms of that? S of P. And we're going to assume the thing I just written earlier. A few lines up, let's head up here. S of N plus P equals S of N plus P. We assume that. Can we prove S of N plus SP is equal to S of N plus S of SP? So that would be 14 to 15. I'm going to have a 13, which is proving this when x is 0. So I guess I should write down, just before we forget it. S of N plus 0 equals S of N plus 0. Remind me to prove that later. Writing over the top probably isn't making it any more legible. So that's going to be an identity block. Overall, it's kind of scary, but each one we're only doing small identity blocks and small stuff. S of N plus SP, trying to prove S of N plus S of P. As long as you trust the structure, trust the process. What do we do here? Well, we probably want to be using this assumption here, so we can turn this into one of these two. We're good. Take this S out the front by just Q4. Now this bit here is this bit here. We're doing this bit here into that. Here's the S. Sn plus P. That's by line 14. Now we'll just stick that S back in again by Q4. We actually proved something. Yay! About bloody time. So if we can prove this iffy statement 13, we are done. We've got a base case and a recursive statement for this, and that allows us to prove the recursive statement for our original claim. So if only it was the case that the successor of n plus 0 was the successor of n plus 0. Well, that doesn't sound completely crazy. Let's try to fill it in. And I guess we've got lots of space here. I'm going to draw a big box, and I won't use all of it. 17. S of n plus 0. I'm trying to prove S n plus 0. Anyone want to call out what the middle line is?
Sn.
Sn. And then this follows from 17 by identity introduction. So each individual rule you have seen before, and that just happened to have an induction that had two inductions inside it. But each induction you've kind of seen before. In fact, the top induction was just E2 written out the second or third time. So this is about as hard as it will get in the exam or in the assignment. And I will say things like, hint, you will need to prove